I'll go ahead and work 2 more examples, and these will both be quite different from the last 2 that I worked. So here we're going to combine the concept of friction and the friction problems with circular motion. So in part A, we're going to calculate the centripetal force instead of the centripetal acceleration, which is exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters per second. Okay, they gave us a lot of information in part A. We have a mass, we have the radius of the curve, and we know how quickly the car is moving. Well, if we look over here again at our equations, it says we're looking for centripetal force, and you might have already guessed this, but that's going to be F with a subscript of C. So we have these 2 options right now. Oh, we have a third option. We have 3 options. So which of these is going to help us answer this question? Let's think about what we have. We have our radius, we have our mass, and 25 meters per second, that indicates velocity. So it's going to make the most sense for us to use this equation right here. Let's write that down. Fc equals mv squared over r. Well, this one's pretty straightforward because we have all of these pieces of information. So let's plug in and solve. And the units are correct too. We have kilograms, we have meters per second. So 900, 25 meters per second squared. And the radius is 500 meters. And again, that is of the curve. So the centripetal force, after you plug this in your calculator, you should find that it is 1,125 newtons. So force, again, is measured in newtons. This was part A. That one was pretty simple. Now let's look at part B. It says, assuming an unbanked curve, find the minimum static coefficient of friction between the tires and the road, static friction being the reason that keeps the car from slipping. So if you think back to the lab you did a couple of weeks ago regarding friction, the static friction was what prevented that block from moving on the metal track. Once it started moving, kinetic friction had taken over. So what is that static friction coefficient, which is keeping the car from sliding off the road when it takes a turn? It says unbanked curve, which simply means the road does not come up at an angle. We're going to assume it to be flat in this case. So here we're going to have to pull in an equation from a previous unit, a previous module, and that one is our friction equation. So you'll have to find that one on your equation sheet. You're not going to find it in chapter 6. So that one's going to be the maximum static friction, that's what that stands for, is the coefficient of static friction multiplied by the normal force. So very similar to that kinetic friction equation. I hope you remember that when we are working with something sitting on a flat surface, the normal force is simply equal to the weight, which is equal to mass times gravity. So we can find that because we have the mass. We know it's a 900 kilogram car, and we know gravity is 9.8 meters per second squared. So then the weight of this car is 8,820 newtons. Now, what actually is our force in this case? Well, we calculated our centripetal force in part A, and that's going to be equal to this force of friction here And that's because the car is actively turning. So it is the force keeping the car in that circular motion that is also going to be the reason the car isn't sliding off the road. So in this case, I don't know why I drew arrows everywhere. These two things are equal, which means all we have to do is plug in the value we got. We're solving for our coefficient, which is this symbol. And then we can plug in our normal force. And we would find that our static friction coefficient is 0.13. And remember, those coefficients of friction are unitless, so this makes sense. Okay, so that problem mentioned an unbanked curve, but I wanted to also show you what it looks like when we have a banked curve. So that just means the road is angled to assist the car with staying on the road and not sliding off. And obviously, the faster you are turning a corner, the more of a bank you would want. This is why NASCAR tracks have highly banked roads. So the banking is just indicated by there being some angle that is greater than 0. Okay, so remember, since it is at an angle, that means that weight suddenly has both x and y components that actually matter. And this is something you might have to take into account. But here, this statement, and I don't know why it got cut off like this, but that should just be over here, equals F net. This is all true for banked curves. So here's some useful information specifically for these situations. So they are for what we call ideal situations. So this is going to be situations with no friction, or where we can at least ignore the friction. When we have friction, we have to do other things, sort of like what happened in the last problem. Okay, so centripetal force equals N sine theta. We know that. It was written above. And we also know that weight is not just going, so normal force and weight will not perfectly equal this time because weight is split into two directions. So now we're going to have to pull out that sine or cosine. And in this case, the weight is going to be equal to N times the cosine of theta. Okay, so this is what mass times gravity is equal to in this case. We can combine these two equations and find that now the tangent of theta, and you don't have to understand where this comes from. You don't need to be able to derive it. Just know that you can combine them and arrive at the conclusion. This combined with other things, that v squared over rg is equal to the tangent of theta. Or if we need to figure out what that angle actually is, it would be the inverse tangent times v squared over rg. Okay, so that's a bunch of information for banked curves. We will quickly look at a problem, but this one's going to be a fairly simple problem now that we've outlined those two equations. And if you notice, the tangent equation is actually given to you on your equation sheet. Okay, so let's work this last problem. Curves on some test tracks and race courses, such as the Daytona International Speedway in Florida, are very steeply banked. This banking, with the aid of tire friction and very stable car configurations, allows the curves to be taken at very high speeds. To illustrate, calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. So we're looking for the speed, or V. This is what we want to know. We have a radius and we have an angle, so it looks like we can simply use this equation. All right, so let's write that down. We have the tangent of theta equals v squared over rg. We would need to rearrange this so that it says v equals, and I'm going to actually do that first. So I'm going to move rg to the other side. So now I'm going to have rg tangent theta. So this is all algebra that I'm doing. Let's take the square root of both sides. When we take the square root of both sides, now we're going to have rg tangent theta under the square root, and then that would just be v. And now we're ready to just plug in. So v equals the square root of the radius, which is 100 meters times gravity, multiplied by the tangent of 65 degrees. And once you've had a moment to actually plug that in, you should find that the velocity is 45.8 meters per second for this particular situation. So those are just a few examples from this module. Hopefully after completing your reading and your concept check, you will feel more prepared to do your check for understanding. Don't forget to email me if you have additional questions. Thanks.